record. Okay, so for those, I forgot to click the record, so let me repeat myself very quickly. So here we're counting blocks. So a blocks is a maximal connected substring of ones in my sequence. So here we have 4 blocks. The problem tells us to use indicator variables to count the number of blocks in a fixed sequence of length n. So what is, when you use indicator variables, we know exactly what to do, right? So you use indicator variables to break down your expected value of your random variable into simpler expected values. So now what is the problem here is defining these indicator variables. And as I've just said, here, how do I know how to count my blocks? And the idea is, well, you care about your neighbors. So for example, I want to count this block here once. So what I could do is say, okay, well, this one introduces my block a block. Why do I know this? Because it followed a 0, right? There was a 0 before this one. So I know that this one introduces a block. So I can look at every one in my sequence and say, well, if you have a 0 before you, you are introducing a block. Otherwise, you're not introducing a block. Now, the only exception is this first guy here. This guy, if it's 1, it will always introduce a block. So that's what we're going to do now. So here, we're going to define indicator variables while being careful about this first one here, this first option. So for x1 is equal to 1 if position 1 is equal to 1 and 0 otherwise. Okay, so if this first position is a 1, I know that it will introduce a block. Now for, let's say, 2 greater or equal to k less or equal to n, like this, I'm defining xk. So for the other position, what do I care about? If the thing before me was a 1. If it was a 1, then I know I'm not a block. So I need to be 1, and I need for the previous guy to not be 1. So at position k, I know that I have a new block if what? If so maybe now, so maybe I can say let's say it like this: if the kf bit is equal to 1 and the kf minus 1. So this is a bit poorly said. I think you get the idea. If you set some notation, you could just say bk and bk minus 1. But here I did not set some notations, so I cannot really do that. So the kf bit is equal to 1, and the 1 bit before that is equal to 0. Equal to 0. So this function is equal to 1 if this happened, and 0 otherwise. So otherwise, xk is equal to 0. Now, the thing that you want to convince yourself about, and in an exam, how do you justify this? So what I'm going to write now is that, okay, x, the number of blocks that I have, is equal to x1 plus x2 up to xn. How do you justify this? You really just say they are counting the same thing. they are counting the same thing. So if you want to be a bit more formal, you would say, well, if this was a 1, so we counted the number of ones that introduced a block. On the right hand side, we counted the number of ones which introduced. And now, once you have done this, well, that's really the hard part of this question. The rest is something that we've done repetitively. So it just becomes, so what do we have? Well, the expected value of x is equal to the sum of these expected values. So this, or yeah, this. Here I'll be a bit careful. The sum from k is equal to 1 to n. These expected values. What are these expected values? Now, these expected values are easy to deal with, right? So the expected value of 1, what is it? The expected value of x1, is equal to what? So what is the probability that my first bit is 1? So as you said, it's a half. Okay, now what is the expected value of xk for is equal, let's say, for k greater or equal to 2, and less or equal to n? What do we have? So for k greater or equal to 2, the expected value of xk, what is it? So now the expected value of xk is equal to the probability that xk is equal to 1, right? That's just by definition of the expected value of an indicator variable. It's equal to 0 times the probability that xk is equal to 0, so that is away, plus 1 times the probability that xk is equal to 1. So I'm only left with this. So maybe I should write it just for clarity. So it's equal to 0 times the probability that xk is equal to 0, plus 1 times the probability that xk is equal to 1. So this is just, again, as usual, this thing here. So now the last question is, what is the probability that xk is equal to 1? Here, okay, well, what do I want? I want the kth bit to be equal to 1 and the k minus 1 bit to be equal to 0. So that's a half times a half. So that's just 1 over 4. And now you go back in your summation. So this summation is what? So the x plus the expected value of x is equal to, okay, it's equal to a half. So I'll pull this first term. So this x minus x1 plus the summation from k is equal to 2, oops, caps lock, k is equal to 2 to n of these tiny expected values, which we found a formula for, which is a 4. What does that make? So how many values, how many times do I add a 4 to itself? A fourth, a quarter. So how does this summation simplify? So this is equal to a half plus what? N minus 1 over 4, exactly. Right? How many values is there from 2 to n inclusively? That's n minus 2 plus 1. So that's n minus 1. And that would be my answer here. Yep.
Why were you able to bring the 1/2 out of the summation?
Why was I? Because I could just put it back in, right? This I essentially, since I started at 2, I essentially said, well, this summation here, I can just pull it out. I can say, okay, well, it's equal to the expected value of 1 plus if I started at 2 instead. It's the only thing that I did. Right? This is true. Right? This plus sign is part of my summation. So it's just the thing is, why did I take it out? Because they don't have the same formula. So I cannot write this unless I take it out. I'm not sure if that's answering your question or if that makes sense. Did that make sense? Yes, no, okay. Silence. All right. Okay, so I think this is I think this is a good question, like the sort of level of the exam, but again, don't quote me on this, but I think that's a good question. It tells you to use indicator variables. So the hard part is really to just carefully define your indicator variables. The rest is pretty much something that we know how to deal with. Every time, that's how you deal with indicator variables. So not too long. I think that's just a right amount. You don't need more than this. So if there's no questions, just continue. I think this one is also a bit faster than what we've been dealing with. So consider the following recursive algorithm, which takes a positive integer n. So what do we do? All coin flips are mutually independent. We flip a coin twice. The coin came up tails exactly twice. We return 2 to the n. Otherwise, we keep flipping. So, okay. You run algorithm tails 1. Okay. Define the random variable x to be the number of the value of the output of this algorithm. So we want the probability that x is equal to 2 to the k. So first of all, 2 to the k is what? What does it represent? So in English, what does it represent? What is this related to? The value 2 to the k. What does it represent in this problem? Exactly, it represents exactly, it represents the total number of flips, right? So k here represents the number of times we had to flip 2 coins. Or sorry, that's not a k, that's an n. So here, if x is equal to 2k, it means this k is the number of rounds we had to do. And when you think about that, then that becomes a very easy question to deal with. So here, what is the random variable? So there's several ways to argue this, but essentially, x, one viable answer would be probably to say something like this. So note that x can be thought as what? Is it a geometric or binomial distributed random variable? Which one? Geometric. Again, why? Because it counts the number of times we did something until the first time we succeeded, right? So we are counting the number of trials until the first success.
So basically, geometric distribution is better used for when we have to get a specific value, and then binomial distribution is better when we have a fixed amount of tries, correct?
Yes, exactly. So in a binomial distribution, you have a fixed amount of trials, and you're counting the number of trials in, of successes in those trials. Whereas a geometric distribution, you keep doing something until the first success. So here the success, so maybe maybe the first thing that you can note is, before noting this, you can say note that 2 to the k represents the number of flips okay, so I think this isn't asking you for the expected value in part A, so I'm getting ahead of myself. So here, maybe a nice answer would be to maybe just say, okay, the probability that x is equal to 2k is equal to the probability that there was exactly k rounds for this algorithm to determine it. Right? If x was equal to 2k, it means that we flip the coin twice k times. Another way, and you could have said that, right? It means it's the probability of flipping the coin twice k times. You could also say that. Maybe I can write it. So which is the probability of flipping coin twice exactly k times. Now, what is that probability? Well, it means this is equal to probability of the first k minus 1 rounds to not give tails followed by tails on the kf round. And now this is pretty easy to deal with. This is 3 over 4 to the k minus 1 times 1 over 4. And why is this true? You can say since probability of tails is equal to the fourth, and probability of so probability of not tails is equal to 3/4. So that would be plenty to say. It's pretty much, it comes down to saying exactly what you would say for a geometric distribution. So part A, pretty standard. So you keep doing something until your first success. What is the probability? So the thing here that you have to understand is k here represents the number of rounds that you have. So the probability that we stopped at k rounds is this thing here. It means that the first k minus rounds were failures, followed by success. So Seb, are you okay, or you want me to repeat myself? Okay, so we are looking for this, right? So the key thing is usually to turn this into a first remark. So this is the first remark. So if you don't like this sentence, you can forget it. Focus more on this one. If x to the k, if x is equal to 2 to the k, what does that mean? It means that I flip the coin twice, exactly k times. So in other words, it means that I had k rounds of this. Right? When I return 2 to the k, it means that on my kth round, I got tails tails, and in every other trials before, I did not get tails tails. So the first k minus 1 rounds did not give tails tails, followed by tails tails on the kth round. So does that make sense so far? Okay. And now at this point, you just use independence, right? So this 3/4 is the probability of not getting tails tails on one round. How many times did that happen? K minus 1 times. Then also, if I stop on the kth round, it means that I got tails tails on that round. So that probability is 1/4. Okay, and that's as much as you need to say for part A. Now for part B, is the expected value finite or infinite? Actually, you can say what it is, right? What is the expected value of x here? One over p. What is p in this case? So what is the number? So if you want to say, so it would be 1/4, yeah? So it would be 1/1/4, which is 4. So part B, I would say something like the following. So you found the probability. Now you don't want to use this formula again, right? You'll get something that looks like a geometric series, which you should know how to simplify. If you want to avoid that, you can say, well, note that x corresponds to a geometric variable with probability success. And again, if you want to say that, if you just, when you say the probability of success, put in brackets, in parentheses, what is the notion of having a success? Here, the notion is getting tail is the probability P of success is 1/4. And then you can say we have seen in class that the expected value equal 1/p for such random variables. Thus, the expected value of x is equal to 1/4, which is equal to 4. And now, let's think about what we struggled with earlier. Let's go back to this question a bit further up here. No, it wasn't this one. Or was it this one? Yeah, it was this one. This was also 4. So this, it's a funny thing, but like sometimes looking at algorithms makes questions a lot easier. Right here, we had to think about, oh, well, if we make one flip, we cannot succeed. And then we thought about this whole partitioning thing. But really, this question you could translate in terms of an algorithm, and then it becomes much, much nicer to deal with. Right? Becomes this. So the expected value of x, which is the expected value of the number of times you have to flip coins until you get tails tail, is equal to 4 times. So I'll just make a note. There, this solution to exercise 3, was it 6.29, right? I think is this one. So this is a much, much, much nicer solution. And it's a good trick to think about. Instead of flipping, if you care about the outcome of 2 flips, well, instead of flipping 1 coin at a time, why don't you flip 2? Right? So instead, if I cared about the outcome of 3 flips, well, instead of I'm going to flip 1 coin at a time, flip 3 at a time. It's much nicer. It gives a much nicer proof. Yeah, so the thing is, it's not, so be careful about what I'm saying. The thing is, this problem, or the problem 6.29 can be translated into this problem. And it's a neat trick. Just instead of flipping 1 coin at a time, you can flip several at a time. So here we flip 2 coins at a time instead of 1, and we stop but we still stop when we reached tails tails. Here we flipped 1 coin at a time, and we stopped when the first time we get tails head. But we got the same exact expected value. And it comes down to the tough part of this question was dealing with the fact that we didn't care about the first coin. And then, well, we were flipping 1 coin at a time. That's what made it ugly. We cared about the outcome of 2 flips, but we were flipping 1 coin at a time. But I guess the trick is to just, if you care about the outcome of 2 flips, why don't you flip 2 coins? And weirdly enough, it becomes exactly the same thing. Yeah, so in the case here, yeah, if we're flipping 3 coins until tails, 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 that would be exactly 8. Why? Because the probability of success. Yes, exactly. So the point is, this is finite because, well, this is a finite number. So if we did the same thing with 3 coins, well, the probability of success is 1/8. So I would get an expected value of 8. And in general, like, I'm not sure if you'll have a questions like this in your exam, but if you're given an algorithm and this algorithm keeps doing something until the first time it succeeds, then to find the running time of your algorithm, the expected running time, you just need to find the probability of success, because then you know it follows a geometric distribution. This kept doing something until the first time telltale happened. So what is the expected running time of this algorithm? It's 4. Whatever 4 units of time mean, right? So algorithm questions are, I think, sometimes they're much nicer than some other counting questions. If you have an algorithm question, don't panic. Just try to think, okay, well, how does my algorithm terminate? And what is this question asking me to compute? And often it comes down to the running time, to the expected number of times your algorithm had to do something until the first time it succeeded. So in terms of expected value, that's what's happening. Okay, finally, this big question, which I'm a bit worried about, to be honest. Because in my head, the part that I'm worried about is giving you a solution that is not the solution intended. So I don't see why this is in chapter 7. That is my problem here. Like, I understand the question, but I don't see why this is in chapter 7. So let me go back in chapter 7 and see what. So I thought we were just talking about graphs. So let's check. So I know the Euler theorem. We have planar graphs, have crossing numbers. So we have a lower bound on the crossing number. And then what? Crossing lemma. We have a lower bound still. So yes, I'm not quite sure. I'm missing something for this question. Okay, so I guess we'll see as I solve. Yeah, I don't know. I mean, the thing is, I feel like Pat has asked a similar question in one of his past assignments, if I remember correctly. And it wasn't a very nice question. It wasn't a trivial question. So the first annoying thing is that, yeah, exactly. So the first annoying part is we are dealing with a round table, right? So that's annoying, but let's read the question carefully. So she's having a party at her house. We have 52 seats. She invites 51 friends. So there's a total of 52 people, and 15 of them drink cider, whereas 37 drinks beer. In this exercise, you will prove the following thing. No matter how the 52 people sit at a table, there is always a group of 7 consecutive people that, such that at least 3 of them drink cider. Okay, so now this is important. From now on, we consider an arbitrary, which is not random, arrangement of the 52 people sitting at the table. Okay, so we picked one. That is the moral here. We picked an arrangement which is not random. That can be the uniformly. So we pick the following arrangement. K be the uniformly random element, a uniformly random element of the set 0, 1, 2 to 51. Consider the consecutive group of 7 people that sit in seats k plus 1 up to k plus 6. Okay. These seats number blah 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 are to be read modulo 52. That makes sense because we're in a circle, right? So for example, if I pick number 49, then I would have 49, 50, 51, 52, but then I don't go to 53, right? I go back to 1. So this modulo part just makes sure that you understand that we're still in a circle, right? 53, and this, if I pick a high enough number, I could go over 52, but we bring it back to something modulo 52. So that's all that it means here. Define the random variable x to be the number of people in this group that drink cider. Okay, prove that the expected value of x is greater than 2. That's it. Yeah, okay. Hint, number the 15 cider drinkers arbitrarily as P1, P2, P15. For each I, we consider the following indicator variables. Okay. So I think this first part looks pretty easy. So let's do the first part. And it's the second part that, like again, I'm not sure why this question is in there, but let's think about it. Okay, so what do we have here? Well, it tells us what the indicator variables are going to be. So like we barely have any work to do, to be honest. So here, x is equal to what? So here I'm counting, I have 7 chairs, and I'm counting, so I'm defining one indicator variable for each person. So I have 7 chairs. If I'm a cider drinker and I sit in one of these chairs, then I count as 1, because that's what the number of people in that group that drink cider. So essentially, this is saying that the number of people that drink cider in this specific group is equal to the sum of these indicator variables, right? I look at each person, and if you sit in this group, then you contribute by 1. So again, this is just, they are counting the same thing. I looked at each 15 cider drinker, and if you were sitting in this group, in these chairs, well, you increase this number by 1. So they are counting the same thing. And now, well, again, it's pretty much a repeat from what we just did, right? So, well, not what we just did, but this exercise here. Once we have our definition of indicator variable, we know what to do. We do use linearity and so on. So the expected value of x is equal to the sum from, I think, the variable I. He uses I use k. So k is equal to 1 to 15 of the sum of these expected values. And this is by linearity of expectation. And what else? Okay, so we work on these indicator variables. So the expected value of an indicator variable, again, it's 0 times the probability that xk is equal to 0 plus 1 times the probability that xk is equal to 1, which is just the probability that xk is equal to 1. Now we think, so what is the probability that xk is equal to 1? Yeah. So what is the probability that Pi sits in K? Or I should say, not in K, but in one of these chairs. Right? I have 7 chairs. What is the probability that Pi sits in one of these 7 chairs? So here it's 7 over 52, right? Because I have 7 chairs. Choosing one of these, if I chose one of these 7, one of these 7 out of 52 chairs, then I was in this group. Here, this is just 7 over 52. For the expected value of x is equal to the sum from k is equal to 15, from 1 to 15 of 7 over 52. And what is this equal to? This is equal to 15 times 7 times 7 over 52. That's equal to 105 over 52. And is this greater than 2? Oh, it's 7 over 52 because I'm looking at one specific person. So what is the probability that that specific person chose one of these 7 chairs? Right, I'm counting the number of cider drinker in this group. So what I did is I looked at each cider drinker and I defined an indicator variable for each of them. If I'm a cider drinker and I sat in one of these chairs, I'm worth 1. Otherwise, I'm worth 0. So the probability that one specific person sits in one of these 7 chairs is 7 over 52. Because I have 7 chairs that I care about over 52 chairs that I could have sat in. So again, this has nothing to do with this chapter, right? So again, I'm not quite sure why is there. So I think it's maybe in part B. So maybe. So part A, pretty standard. And now we're done, right? Because this is strictly bigger than 2. So what about part B? Okay, part B. For the given arrangement of the 52 people sitting at the table, prove that there is a consecutive group of 7 people such that at least 3 of them drink cider. So we have one arrangement. We want to prove that there exists a consecutive group of 7 people such that at least 3 of them drink cider. Okay. So again, I don't see the point. So I'm just scratching my head because I don't see the link in this chapter. So here, assume the claim is false. What is an upper bound on E of x? So to be honest, like to me, certain people. So here, what did we show here? Let's just understand part A. Part A, we showed that, okay, if I consider a group of 7 consecutive chairs, in that group, I'm expecting to have at least to have more than 2 people in this group to be drinking cider. So does that imply part B? Yeah, we'll just push through because again, in my opinion, I really don't see how this question relates to this chapter. So here, and I don't even see the hint, to be honest. Like, to me, like, we're pretty much done. Yeah. The thing is, there's almost no questions in chapter 7 from the textbook. There's only 8 questions in this chapter, so yeah. So one thing that you should probably know from chapter 7 is the formula, Euler formula, and maybe the crossing number, which of a graph. So why? Because you could have a question like prove or disprove that K5 is not planar. And if you know your formulas, that's one line, right? I doubt you would have a question more difficult than that. Prove or disprove that a graph is planar. Probably something like that. If you have a question on chapter 7, yeah, I doubt it would be more difficult than that. So maybe let me double check. So, okay, we'll take a break. Let me double check what Professor Sack told me. So the topics, and I'll come back to you. But I'm pretty sure that's as far as it goes for chapter 7. So again, another break.